this is Tiago from Coderversity, and in today's video I'm going to be teaching you how to develop some algorithms that you will need to nail that interview that you are so anxious about. In this video you will learn how to develop sorting algorithms, searching algorithms, recursion and backtracking algorithms, graph algorithms, and some dynamic programming, and for that we will be using C#. So what are we waiting for? Let's dive in. So let's start by creating the project. I'm using VS Code, but feel free to use an IDE of your choice. So let's start. We'll be using .NET C#. And for that, since it's a real logic-based project, let's use a console app. Let's put it on desktop. Let's call it interview algorithms. Okay, let's create a structure. Let's start with a folder for the sorting algorithms. So let's start with a bubble sort. Let's create a file and a public static class bubble sort algorithm. Now, what is a bubble sort? A bubble sort is a simple comparison-based algorithm. Let me go to the browser so that I can draw while I explain. It works by repeatedly stepping through the lists, comparing adjacent elements and swapping them if they are in the wrong order. So this process continues until the list is sorted. The bubble sort is easy to understand, but it's not the most efficient sorting method, especially for large datasets. So let's imagine. We have here a list. And then we have here numbers, a 2, a 1, and sorry for my drawing, a 3, and a 4. This is the index 0, as all the arrays start. Then the index 1, the index 2, and the index 3. So the index 0 has the value 2 of the list, the 1 has the value 1, the index 2 has the value 3, and the index 3 has the value 4. So how does the bubble sort work? We go from the index 0 until this one, until the last index. And then we want to compare if this element in the index 0 is bigger than this one, then we swap. So what would be the output? You guessed it. It would be 1, 2, 3, and 4. The indexes are always the same. And there we would have our list sorted. And this would be for every element. So after we compare the 2 with 1, we will swap because the 2 is bigger than 1. Then we compare in this case, the 2 with the 3, and then the 3 with the 4. But we don't swap because the 2 is lower than the 3, and the 3 is lower than the 4, and so on, so on. So let's go back to the code. Let's start by declare the method public static void bubble sort. We receive an array that will have all the elements, and then we can type in a for loop, starting with the index 0. That, as we saw, all the arrays start in an index 0. Then we will go from our index until the end of the list. That is array. What is the end of the list? It's this one. And how do we achieve this one? It's the length of the array, that in this case is 1, 2, 3, 4, but we want the index since we are working with indexes. So it's always length minus 1, because don't forget the indexes start with 0. So to get the length, we get array dot length minus 1. And then for each iteration, we increment the I. This is to outer loop, for the outer loop. Oops. This is for the outer loop to traverse the entire array. Now, what do we need? We know that we want to traverse all the elements. But if we do that, we are just comparing these ones, right? So we are going to, with the 1, we compare, we switch. But then we are comparing the 1 with the 3, and we don't want that, right? And the 3 with the 4, etc., etc. So we want an inner loop. So we want to compare the adjacent elements. So we want an inner loop to compare the adjacent elements. So we declare another for int j equals, let's give it another variable, and the j goes on until the n, until the array dot length minus 1. But then we don't want again to compare to the last one. We want to compare all of these, and then we don't want the last one. We just want to compare the last until the last one, and then until this one, until this one, and until this one, until we finish the array. So firstly, we compare to this, then to this one, then to this one. In the next one, we compare to this one and to this one, and then to this one, and then we have the last element and the list is ordered. So let's do it. So here we have the j equals 0 and the j until while the j is lower than the array dot length minus 1, that is while it's in the last index, but as I said before, we want always the index before the last one. And how we do achieve that? We have the I, right? So in the first iteration of I, we will iterate all of the iterations of j until we reach this condition. So I forgot this. So if I put like this, it will always be the same. So we will, for each iteration of the I, for the 0, for the 1, for the 2, and for the 3, we will compare the j until the last index, and we will have an unnecessary loop. So we want to have the 0, the 1, the 2 until the 3, and in the next loop for the 0 to the 1 and to the 2, and then to the 0 to the 1, and then only the 0, and the list is ordered. So it's array dot length minus 1 minus I. What does that achieve? after the whole iteration of j, di will always be 0. So for di0, it will be a whole cycle for j, and the first cycle, it will be to the array dot length minus 1 minus 0. So it's until here. Then di will be 1. So the j will go from 0, from the beginning, until array dot length, that is 4, 1, 2, 3, 4, minus 1, that is the index 3, minus I, that is 1. So 3 minus 1 goes 2 and goes to this element. And then, again, the I becomes 2, and then the j goes from 0 until array.length, that is 4, minus 1, that is 3, minus 2, that is 1. So we come from here, and so on, so forth, until the list is ordered. So let's put it like this. So let's order. If we find, like in this example, the 2 is bigger than the 1, we want to switch, right? So what do? We do array j, right? Because we always want to compare the index of j, because we are only using I for to traverse the entire array, and j to compare the adjacent elements. And then if array j is bigger than array j minus 1, so in the next index, we switch array j equals to array j plus 1. But does this work actually? I don't think so, right? Because if we change the value of, let's say j is in the index 0. So let me erase this. So here, let's put 3, 7, 2, 4. Let's say the j is on 0. If j is on 0, we don't swap, right? Because this is lower. But then j is on 1, and the value in the index 1 is bigger than the value in the index 2, correct? So we have to swap these. But what happens if we do this? The array j, that is the array in index 1, becomes the array in index j plus 1, that is array 2, that is the value 2. So we replace this value with 2, but then we lose the 7. So it becomes the same thing. But like this. And now we lose the 7 because we didn't save this before. So we have to take care of that. So let's save it in a temporary variable. This way we don't lose it. And now the array j plus 1 equals temp. And this way we make a good switch. And there we go. We have a bubble sort. But don't worry, in the end we will test all of the bubble sort. All of the algorithms, sorry. Next up, we have the quicksort. The quicksort is a highly efficient sorting algorithm that uses the divide and conquer approach. The algorithm selects a pivot element from the array and partitions the other element into subarrays. Those less than the pivot and those greater than the pivot. The subarrays are then sorted recursively. This process continues until the entire array is sorted. So let's imagine our array, our pivot is, let's say, 4. So we choose 4 as our pivot. So let's choose 4 as our pivot and move it to the last position. Okay, then the conditions that we have to comply are those in the left. We have to switch with those in the left with that are less than the pivot and those in the right that are higher than the pivot. So let's say what is the one in the left, so in here that is higher in the pivot, sorry. So we have to switch the higher in the pivot on the left with the lower with than the pivot on the right. So on the left, which one is higher? I would say 7, right? So we switch 7 with 1. So the array stays like this. And then we have on the left, so we don't count this anymore. I mean, for this iteration at least. And then we have on the left, we have the 7, and the lower than the pivot on the right will be the 2, correct? So we swap them again. So the array becomes like this. And now we can't do anything else, because on the left we have 1 and 2 that are lower than 4, and on the right we have 7 and 5 that are higher than the 4. So what do? We have to switch the higher, that is 7, and the 4. And then it becomes like this. Becomes something like this. 1, 2, 4, 5, and 7. In this case, it's already ordered. But let's say it wasn't ordered. We just let the recursive handle the rest until it is ordered. So we would choose another pivot and repeat the same process. So let's get to the code. Let's create a new file for the quick sort. And declare public static class quick sort algorithm. Declare the method. So we receive an array like this one, and then we want the lower, where is it? Then we want the low on the right, and then the high on the left, on the left. And then these we are talking about the indexes. And then if the number on the low indexes is lower than the number on the higher index, then we need the partition index and to check if the partition index is now at the right place. So let's set pi as the partition index and call the method partition that I will do in a second. Oops. And hi. Let's create a partition. So this is the condition that we saw when we already filled the conditions and we had to switch the pivot with the other number that was higher than the pivot on the left. So let's create the partition. So let's create a static int partition where we receive the array, the low index, and the high index. So this method is to take, as I said, the last element as pivot and it places in the correct position. So, and it places all the smaller elements to the left and all the larger elements to the right. So the pivot should be the element in the higher index. So pivot element, and then in the I we should get the one on the index of the smaller elements. Why is this -1? We will see up next, no worries. Then we will have to traverse through all the elements and compare with the pivot like we did just here. So we compare to all the elements to check if they are on the left, to check on the left if it's lower or higher, and on the right if it's lower or higher as well, and switch them if necessary. So let's do it. So if the current element is smaller than or equal than a pivot, then we will swap, right? So we will remember that I said -1 just for this. We will increase the I here, and then we swap and use a temporary variable like we did in bubble sort, and swap the two elements. Okay? Then, after we iterate, we have to swap the array I plus 1, sorry, and the array with the high element, or known as pivot. So in here we are saving, we just are doing just like in here, we are saving the temporary variable, then we are just swapping. And then we just return the partitioning index. We return the partitioning index. Then the method for the partition is done. Now that we have our partition, we need to recursively sort the elements before and after the partition. So let's call again the quick sort and take the array with the low elements before the partitioning index -1, and then call it recursively again after the partitioning index. So here it's before partitioning index, and here after the partitioning index. And there we go, we have a quick sort. Don't forget, we will try them all. As long as you understood the algorithms, don't worry, we will try them all once they are all done. Introducing now the search algorithms, let's start with the binary search. Binary search is an efficient algorithm for finding the position of a target element within a sorted array. It works repeatedly, dividing the search interval in half. If the target element is less than the middle element, the search continues in the lower half. If it is greater, the search continues in the upper half. This process continues until the target is found or the interval is empty. Binary search significantly reduces the time complexity compared to linear search, making it much faster for large datasets. So let's put our hands into it. Let's say we have here an array, a sorted array of course, of 10, 15, 27, 30, and 40. We will start in the middle. So the number, let's say the number we want to find is 30. Okay, actually let's put it a bit bigger. Let's add a bit of numbers, 57 and 60. And let's say we want to find 57. So we want to find 57. So the binary search starts with the middle. Is the 57 higher than the middle? Yes. Then we will search on the datasets to the right. Then we will get the middle of the dataset to the right. Is it 57? Yes. Then it returns. Otherwise, it will just repeat the process until it finds. So it doesn't waste time searching for, in this case, lower numbers. So let's put our hands into the code. Let's create a folder here for the searching algorithms. Let's create here a file and let's call it binary searching.cs. Public static class binary search algorithm. Public static and return an int binary search, in which we receive the array we want to search in, the left index and the right index, and then the element that we want to search. So let's start. Our stopping condition is if the right element, I mean, in this case it's not stopping condition, it's more like the continuing condition, because if the right element, let's say we pass by parameter the end of the array and in the left the beginning of the array, we want to say if the beginning, the end is higher than the beginning, then it means we didn't search the whole array and we want to do it. So we want to find the middle, like we saw in the drawing, and the middle is, this is a formula, and it's the left index plus the right minus the left divided by 2. So let's put that in practice. Let's say we have an array with the index 0, 0, 1, 2, 3, 4, 5, and 6. And 7 to be a pair since it starts in 0. So how do we find the middle? And let's assume that we pass the 0 and the length minus 1. So the middle will be the left, that is 0, plus the right 7 minus 0 dividing by 2. Actually not 7, this is 8. So since this is a division, it will be 8 divided by 2, that is 4, plus 0, that is the left. So 4 will be our middle. And it's correct. Then we will check if the element is present at the middle itself. So if the array in the index of the middle equals to the element we want to search for, then we return the index of the middle. That is the index that we are returning. We are returning int because we are returning the index that we can find the element we are searching for. And then, if the element is smaller than mid, we search the left subarray, and we can call it recursively. So if the array mid is higher than x, we return binary search that we'll call recursively and repeat the process with the array beginning in the left and ending in the middle, because we want the left subset of the middle since it's lower than the element we want. Otherwise, it will just return the same thing, but to search the right subarray. Pass the array mid plus 1, because it starts on the right, since we decided that the mid minus 1 is for the left, and then the mid plus 1 is for the right. We pass the right and the element we want to find. And then the recursiveness takes care of the rest. If we don't find it, because it can happen, we return -1, which means the element is not present in the array. And there you go, you have a binary search. Stay tuned, linear search is next. Linear search is the simplest search algorithm. It checks each element in the list sequentially until it finds the target element or it reaches the end of the list. Although it's not as efficient as binary search, linear search is straightforward and can be used on both sorted and unsorted arrays. It's the most useful for small datasets or when the list is unsorted. So let's begin. Let's create a linear search it's yes, and public static class so let's perform it. Public static int linear search int dot array. We want the array and the element and that we want to find. Back to our drawings. Let's say we have, let's say that we have here an array and it has multiple elements. We have here a 7, a 2, a 3, a 4, and a 1. And we want to find the element 4. The linear search is very simple. It looks on the first element. Remember, we want to search for the 4. Search for the first element. Is it the 4? No. Goes for the second. Is it the 4? No. Is it the 4? No. Is it the 4? Yes. And then it returns. Simple as that. So, let's continue on our code. So for that, we have to have a cycle that will traverse all the array. So we start in the first index that, you guessed it, starts on 0 and goes until the index is equal or higher, not higher, is equal the array length. When the index is equal to the array length, it stops. And then we increment. And then we simply check if the array in that element equals, in that index equals to the element we want to find, then we return the index. Otherwise, it traverses all the array and doesn't find, we return -1. Simple as that. You have a linear search. Next on the list, we have the recursive and backtracking algorithms. Let's do a factorial calculation. We will do an iterative and a recursive way. So what is a factorial? The factorial of a non-negative integer n is the product of all positive integers less than or equal to n. Factorials are used in various mathematical computations, including permutations and combinations. Factorial can be calculated either iteratively, by multiplying numbers from 1 to n, or recursively by multiplying n by the factorial of n minus 1. So, as an example, let's say we want the factorial of 3. This is how you represent a factorial. So, how do you calculate it? Factorial of 3 is the multiplication of all the positive integers, as I said, from 3 until 1. So it's 3 multiplying by 2 multiplied by 1. That is 6. If it's the 4, then we will have 4 multiplied by 3 multiplied by 2 multiplied by 1, which gives 24. Then let's start with the iterative way of programming it. So let's create, again, like you already used to, create a folder for recursive and backtracking algorithms. Let's create an iterative factorial calculation. This is very common in interviews, so pay attention. Public static class iterative factorial calculation. public static int factorial of the number we want to input. The result, we can start with 1. Let's initialize it with 1. And then we will increment from 1 until the n. We will assume that n is a positive integer. Then we cycle from int I equals 1 until I is less or equal than n, because we want to include the number that we want to calculate the factorial. So for example, we want a factorial of 3, we want to multiply 1 times 2 times the 3 itself and increment each iteration by 1. And then we multiply it with the result with the I. So the first time, let's say the n is 3, the first time it will multiply the result that is 1 with 1, that stays the same, then with 2, and then with 3. That will give 6. And then we just simply return the result. This was the iterative way. Now let's do the recursive way. Let's create a new one. Recursive Factorial Calculation.cs. Public static class cursive factorial calculation. Public static int factorial of int n. And then, what is the stop condition? We will start, since it's a recursive, we will start by in the n and go until the 1. So our stopping condition in a recursive will be either if the n equals to 0, because it's not possible, or the n equals to 1. Because actually the factorial of 0 is 1. It's a mathematical rule. So if n equals 0 or n equals 1, it's always 1. So since we're going from the higher number to the 1, this will be our stopping condition. Otherwise, we will just return our number versus, and then we call again the factorial n minus 1. The recursive case. So let's say it's 3 again. It's 3. Then it's equal to 0 or equal to 1? No. Then it will be 3 times factorial 3 minus 1, that will be 2. Then we have a call here that will be 3 times factorial of 2. And then what will factorial 2 translate to? It will be this n, that is 2, times factorial of 1, that is, when it equals 1, it's 1. So 2 times 1, so it's 3 times 2, that is 6. And there you go. We have all the cases covered. And there you go. You have the recursive way as well. The Fibonacci sequence is next, and we will have an iterative and recursive way as well. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, usually starting with 0 and 1. That is, the sequence begins with 0, 1, 1, 2, 3, 5, 8, 13, and so on. The Fibonacci sequence can be calculated with a simple recursive approach, but this can be inefficient for large inputs due to the overlapping subproblems. A more efficient way to compute Fibonacci numbers is by using dynamic programming. This approach stores the results of subproblems in a table or array so that each subproblem is only solved once, reducing the time complexity from exponential O of 2 elevated to n to linear O of n. In summary, the Fibonacci sequence is a series where each number is the sum of the two preceding ones. So, let's say we want to check the Fibonacci sequence until the number 13. So it starts with 1, with 0, and then 1. What's 0 plus 1? It's 1. What's 1 plus 1? 2. 2 plus 1, 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13, and so on. So, let's translate it to code, shall we? So, let's create a folder. This is dynamic programming. Let's first start with an iterative way of doing it. As always, public static class Fibonacci iterative algorithm public static int Fibonacci. I misspelled here and here. And we want the n which we want to calculate. So if our n, that is the number we want to achieve, it's less or equal to 1, we return it. In the base cases, Fibonacci of 0 and Fibonacci equals 0 and Fibonacci of 1 equals 1. So, as I said before, this solves each subproblems. So, we will have three variables: int a that will equal 0, the b that will equal 1, and c equals 0. Why? Because the first one, the a, will always sum to the next one. That will start always with 1, so 0 plus 1, as you could see in our example. And then the sum of these two will be stored in C. Then the A becomes the B. As you can see, like we did here, this was our A, and then this was our B. We summed this, and we got our C. Then our A was this one, and this was our B. And then the sum of these were our C, and so on and so forth. So let's continue. So since we will have already the sum of 1, we can start in 2 until we reach the number we want to calculate, until iterating by 1. As I said, our C will be our A plus our B, that will calculate the next Fibonacci number, and our A will become our B, and our B will become our C. And then we will just return our C. And that's it. You have a Fibonacci iterative. Now, let's get to the recursive way. Let's copy paste to save some time. Recursive Fibonacci sequence. .cs, recursive, and then let's erase the code, and we keep the return and the input. So same condition, same stopping condition. If the n is lower or equal to 1, it means we stopped and we reached the end, so we return the n. Otherwise, we will just calculate what the two previous numbers, right? So we call the Fibonacci again with our number minus 1 plus the Fibonacci n minus 2 because we are going backwards. So let's say we are going 0, 1, 1, 2, 3, 5, and 8. We are going from 8, that is our n, and then summing the 5 plus 3, and then the 3 plus 2, and 1 plus 1 until we reach the n equals or lower than 1. And then we have our Fibonacci. And lastly, we got the graph algorithms. We will start with the breadth first search, also known as BFS. So the breadth first search, or BFS, is a graph transversal algorithm that explores nodes level by level. Starting from a source node, BFS visits all its neighbors before moving on to the next level of nodes. This approach ensures that BFS finds the shortest path in terms of number of edges, from the source node to any other node in an unweighted graph. Nodes are marked as visited once they are in queues to prevent revisiting them, which ensures that the algorithm efficiently traverses the graph. In summary, BFS explores nodes level by level, starting from a given node and visiting all its neighbors before moving to the next level. It is particularly useful for finding the shortest path in unweighted graphs. BFS uses a queue to manage the nodes to be explored. So let's draw a little. Let's say we have a graph. A graph is a group of nodes that are connected. So let's say we have the node 1 that is connected to the node 2 and 3, and then the node 2 is connected to the node 4, and the node 3 is connected to the node 5, 6, and 7. And also the 7 is connected to the 8. How does breadth first search work? So it searches in horizontal way. It starts with this node. Let me put here a different color. So it starts with the node 1. Let's say yellow is for visited. And let's say that the green is for unqueued, which means we will have to visit it next. So we will start the one that is already visited. What are we unqueuing next? The neighbors, right? The ones that are directly connected to the one. So we will unqueue 2 and we will unqueue 3. And what is the next one to be visited? Yes, the 2. And then the 3. And then we will dequeue the visited ones, like I said before, to not visit them again. So the visited are dequeued and the visited and the ones to be visited are inqueued. And a queue is like a list that you can pop the last element. So let's enqueue the next ones. So we have visited the 2 and the 3, so we will enqueue the neighbors, which are at the same level, that is BFS, the 4, 5, 6, and 7. And after, we will visit, and once visited, they are dequeued or popped from the queue, whatever you want to say. And lastly, we only have D8 that will be enqueued and later visited, of course. So let's put into practice. Let's start here with a new folder for the graph algorithms. Let's put it bfs.cs. Public static class bfs. Public static void bfs. And then we will choose a dictionary, and I will explain why in a bit. We will have the graph here and the start node. Why? Because a dictionary has a key, and the value that in this case will be a list. So our key will be a node, and our list will be the neighbors, which means the nodes they are connected to. So in this case, if our 1 is the key, the 2 and the 3 will be the list that we want, or the neighbors per se. So that will be our graph. And we will have an entry for each node. Then we will of course have our queue, which will contain the nodes. And then our hash set. A hash set is a list. It's like a collection actually, where we can only have distinct values in it, which we will store the visited, because we can't visit the same node more than once. So it's the ideal collection to use. Then we will of course enqueue the start node, and of course, like we did in the example, add to the visited. Then, while the queue has nodes, we will visit and pop them from the queue to not visit them again. So while the queue is not empty, which means that has a count higher than 0, our current node will be the one that we dequeue before, and let's write the current node we are in. And leave it a space for the next ones. Then, so the current node in this case will be the start node, but after the next visits it will be others. So next we will visit all the neighbors of the current node, like we did in the example as well. So neighbor in the graph, and how do we get the neighbors? We go to the graph, that is our dictionary, and this is not int, it's in, and we type in the key that will be our node, that will be current node, and this will retrieve our lists, that will be the list of neighbors of that node. So if we didn't visit that neighbor, so if the visited hash set doesn't contain the neighbor, which means if we didn't visit it, we will enqueue it, and here is not a comma, it's a dot, and then you guessed it, we'll mark them as visited neighbor, and there you have a BFS. There you go. For the last algorithm of this video, let's do the depth first search DFS. The depth first search is very similar in terms of way of searching to the breadth first search and a bit simpler in code-wise. So the depth first search will be also a graph. So let's draw here the same graph more or less like we did before. 1, 2, 3, 4, 5, 6, 7, and 8. Let's do like this. On the contrary of breadth first search where we explored by levels, the depth first search, like the name suggests, searches by depth. What does that mean? So starting node in 1, we have to queue the 2 and the 3. So let's enqueue them. We will enqueue the 2 and the 3, and we will visit in depth the 2, and then we will continue, but this time we won't do like in horizontally, we will do vertically. Next we will go to the neighbors of 2, that is 4, and now we have 4. We enqueue them, now we visit it. Now 4 doesn't have neighbors, so we go to 3, we visit 3, and then we enqueue all of its neighbors. For explanation matters, let's remove here the 8 and put in here so that you can understand better. So now we have the 5, 6 and 7. What do you think we will search next? Of course, we'll visit 5. And now what happens? What we will enqueue or visit? Remember, this is a depth first search. You guessed it. So we will enqueue the 8. And of course, we will visit it since there are no more neighbors. And then we will go to 6, and then 6, since 6 doesn't have neighbors, we will go to 7. So this goes a bit more vertically. So let's put that in practice. Let's call it DFS. Let's go public static class DFS algorithm public static void DFS, and we receive more or less the same input, our graph, that will be the node and its neighbors, a list of it here. will be our graph. Then the starting node and the hash set of visited, because we will need this, because we will implement this recursively. So we have the node, and now we will start by visit the current node. So we will add to the hash set the current node, and we will write the node that we are in. Then we will visit all the neighbors of the current node. So for each neighbor in our graph of that node, so we'll get the list, putting our node using it as a key, and then if we haven't visited that neighbor, so if the visited hash set doesn't contain our neighbor, means we didn't visit that neighbor, we will call DFS and it will go through all the way through vertically, because it will give priority to the neighbors like we saw here. So the one has the neighbors 2 and 3, and then we call again the DFS to the 2 and then to the 4, and once it processes the 4, it goes back to the 2, goes back to the 1, and goes to the 3, and so on and so forth. And visited. And simple as that. You have a DFS. I've made here a menu where we can try all of our algorithms, and now let's go through them. So let's run it with a terminal. Let's run. There we have a menu to check what we want to use. Let's start with the bubble sort. For the bubble sort, it's a sorting algorithm, as you already know, and we use this array. It will sort it using the bubble sort algorithm, and it will print out. Let's press it. As you can see, it's sorted. It was unsorted here, and it's sorted now. Let's go back to the menu. The quick sort. We have here this unsorted menu, and let's try. There you go, it's sorted too. Now, the binary search. We have here all these elements, and we want to search for 7. And it will print the index that we can find the 7. Found at index 3. 0, 1, 2, 3. Correct. So now let's go to the linear search. The linear search, we have the target 10 that is in the index 0, 1, 2, 3. Linear search, index 3. Correct. Now, the recursive factorial calculation. So let's 5, and we know from before that the factorial of 3 is 6. And we also know from before that the factorial of 4 is 24. Let's try now the iterative way. 3 and 24. Careful not to use very large integers, because the integers have a range that they can store numbers, so they might blow up, let's say like that. So let's try now the breadth first search. The breadth first search, we constructed here a graph that the starting node is 0 and connects to the 1 and 2, and then the 1 connects to 0, 3 and 4, and the 2, 0, 5 and 6, and so on, and we are performing the BFS starting from the node 0. So let's do it. So 0, 1, 2, 3, 4, 5, and 6. You can try them on your own, you can write your own examples, and you can play with it for a while. Let's try now, lastly, the DFS for the graph algorithms. The 0 for the 1 and 2, it's the same graph. 8, 0, 3, 4, 2, 5, 6. You can see it's a different output since we visit it in a different way, as you already know by this time. And now the Fibonacci. The Fibonacci, let's go until 10 in an iterative way. I put here an 8, but it's a 9. It's 55. And then let's try the recursive Fibonacci sequence, also for 10. There we go. And that wraps up our tutorial on developing interview algorithms. I hope you found this project helpful and that you learned something new along the way. If you followed along, congratulations on completing the project. Don't forget to like this video if you enjoyed it and consider subscribing to the channel for more programming tutorials and projects. If you have any questions, suggestions, or just want to share your own version of the project, drop a comment below. I'd love to hear from you. Thanks for watching and happy coding! See you in the next video.